Hey guys, so our first review quiz I'm going to go over just so we don't have to spend time in class. You can see and pause and read here all of these explanations. So the need to know stuff, so area under a force time graph. Well, area will always be the two variables multiplied by each other, so that's going to be force times time, like this. And if you're looking at your equation sheet, oh crap, where did I put it? Okay. If you're going to look at your equation sheet, you're going to look for force being multiplied by time, and you're going to find right up here that the change in momentum is equal to force times time, so that was your first answer, change in momentum. And if you just put momentum, that's actually incorrect, because I could have a momentum of 1 million, but if I have no force applied, then my change in momentum will be 0. I'm staying at the same. You also will remember that this is also called, aka, the impulse on an object. The slope of a position versus time graph. So anytime you're finding slope, that is the first variable over the y over x, rise over runs. That's change in position, which is x, over the time. So change in position or displacement over time is going to give you velocity. So that's partly you could know that, just the definition of velocity is how fast, how much your position is changing each second. Or you could think, okay, this is measured in meters, that's divided by seconds, meters per second, that's velocity. 3, the velocity of an object at the top of the angled projectile in terms of v, the initial velocity, and theta. So if you think about if something is launched with a velocity v at an angle theta, I'm talking about the velocity at the top. A lot of people got this wrong because they're like, ooh, velocity is 0 at the top. Your y velocity is 0 at the top, but you still have an x velocity because your x velocity is constant, meaning it's not changing. So my x velocity, I still have vx at the top, and your x velocity is just going to be v cosine of the original angle. Because at the very beginning, you would break it up to v cosine and v sine. Well, v sine is the y. That's already gone to 0 at the top, so it's only the x velocity, which is still v cosine because it's constant. There's no acceleration sideways. There's only the acceleration down, gravity, because the only force acting on it while it's in the air is gravity. If an object has a negative velocity and a negative acceleration, so negative v, negative a, that means, so let's say it's to the left. If your velocity and your acceleration are in the same direction, that will always be speeding up. Some people think negative acceleration is slowing down. That's actually not the case. It depends on just, is it in the same direction as your velocity or not? That tells you if it's speeding up or slowing down. The slope of a velocity versus time graph. So this would be change in velocity over time. So one way to do this is just think about the definition. So how fast velocity is changing per second, that's the definition of acceleration. A lot of people I saw thinking through units, so that would be meters per second over seconds again. 2 seconds on the bottom, that's meters per second squared, which is acceleration. You also could have looked the first equation in your equation sheet. If I'm looking to solve for A, see how you'd subtract the velocity over, that's change in velocity, and you divide by time, change velocity over time, that gives me acceleration by the first equation. The area under a velocity versus time graph, so that would be velocity times time. So this would be meters per second times seconds. Those seconds, the dividing and then multiplying by seconds would cancel out, giving me meters. Some people went that route. You also could think about it in terms of v times t is going to give me delta x. That would work. Most people do the unit stuff, so velocity times time is going to give me displacement. Or the change in position, that would all work. The distance, change in position, displacement. The area under a force time graph, so again, area would be multiplying. Force distance would be FD, or even if you have F delta X, you might not see F delta X on your equation sheet, but you know that delta X is displacement, which can be like a distance as long as it doesn't turn around. And if you look for force distance, you'll find that that is equal to the work, which is also equal to the change in energy. So I would have taken either answer. Most people said work, or slash, that is also the change in the energy. Not the same thing as energy, because, right, if you have the constant energy, right, that's not you could have a ton of energy but have a zero change in energy if you don't have any forces applied. All right, what equation gives you average speed of an object or the velocity when it's at constant velocity or constant speed? That's just v equals c over t. That's something you should have memorized because that is not on your equation sheet. All right, number 9, the following graphs, all drawn to the same scale, represent the net force F that as a function of displacement for an object that moves along a straight line. If the object starts from rest, which graph represents the force that will leave it moving fastest at the x1? So I want to know which of these graphs at the very end of the path is going to have the greatest speed. A lot of people chose C because they were like, oh, this is getting steeper. And if this was a position versus time graph, then totally getting steeper means it's moving faster. But it's not a position versus time graph. It's a force and distance graph. So if you're looking at force and distance, you can either find the force at a point, you can find the slope of the graph, which would be force over the distance, or you can find area under the curve, which would be force times this, which looks like FD on your graph, because this is just like the displacement, the distance. So I know that the area under the graph is going to give me the work done on the objects. Now I'm thinking through, okay, what does work have to do with speed? Well, work is also the change in energy. And in this case, if it's moving along a straight line, it's going to be the change in kinetic energy. It doesn't say anything about it increasing in height, so it wouldn't be increasing in potential energy. It's just a force that is causing an object to accelerate, causing it to speed up. So the work would also give me change in kinetic energy. Well, I know it starts from rest. My kinetic energy at the beginning is 0. So the one that has the most kinetic energy at the end is going to be the one that is going the fastest. Because we're still talking about just one object, so the mass would be the same for each. The only thing that's different is the amount of force applied over a distance. So the one that has the greatest amount of work will be going fastest at the end. Well, work is area under the curve. I don't need to actually do any calculations. You can tell just based on sketching in the area under the graph, the one that has the most work done is going to be T. It has obviously the most work put into it, so if they all start at rest, the one that has the most work put into it has the most kinetic energy at the end, so it'll be going the fastest. Number 10, so we want to look to rank the displacement during the 3 segments. So this is a velocity versus time graph. Velocity versus time, to get the displacement, that's just going to be the area, because velocity times time is going to give me delta x, because v equals delta x over t, slash that's what we set up here. So I'm just going to break it down into the 3 segments. So this would be one segment, this right here is another segment, and then lastly I've got this one right here. Now I watched a lot of people when we were taking this quiz in class spending a lot of time actually calculating. And there are some ones where you actually would have to calculate to tell, but here, because I'm just ranking it, I can actually just look at these colors and I can tell immediately which one is greater. So if I just look at 1 and 2, 1 and 2 are both triangles, they're both the same height, and they're both, they're both too wide, but this one actually isn't a triangle all the way down. It's, I can't remember what it's called, trapezoid, I think. Anyway, it doesn't matter. Number 2 definitely has more area than number 1, because if it was equal, it would just go straight down to the 0 right here, and it gets a little bit more area. So already I know that 2 is more than 1. And then now if I'm looking at 2 and 3, well, 3 is definitely more because it's higher. It's going to have this little extra area up in this section right here. So then 3 is even more than that. And then it's also asking, how does that compare to 0? Well, let's look. I have positive areas. It's tempting to think that 2 might be a negative area because it's decreasing, but a decreasing velocity just means it's getting slower. I can be in my car getting slower and still be moving forward and be have positive displacement. So these are all positive displacements. So all of these were greater than 0. So the displacement in 3 is greater than 2 is greater than 1, and all of those are positive values more than 0. Number 11. So here we're deciding which of these is true. Again, this is a velocity versus time graph. A is not moving from time 4 to time 10. So that would be this section right here. It's definitely moving, has a velocity of 10. Your velocity would have to literally be 0, at this instant and this instant, for it to not be moving. So this one was not correct. The initial and final positions are the same. So if you look from here to here, I know my velocities are the same. That is not the same thing as final. So let's just think, could this make sense? Well, I have positive velocity for a while, and then I have negative velocities for a while. So it could be possible that I am ending up back where I started. In order to know for sure, I would have to actually calculate, because I can't just look at this area compared to this area and decide, like, yeah, that's the same or not. So we'll come back to B. That is a possibility. C, it says the object is slowing down from 14 to 16 seconds. So 14 to 16 is this section right here. This is a velocity of 0, and then it's going to like -1, -2, -3, -4, -5. That is increasing in speed. That is getting faster. It might be going down, but it's going down in the negative direction. It's getting farther away from 0 velocity. Anything farther away from 0 velocity is going to be faster. So that's not true. It's getting faster, just in the negative direction at that time. And then the average acceleration from 0 to 4 seconds is different than the average acceleration from 34 to 36. So if you notice, this is 10, and there's 5 like tick marks, so this is the first 4 seconds, these two. And then the last 2 seconds, 34 to 36, is this part right here. So I'm going to actually calculate, because like these look like they're roughly the same steepness, but I need to actually calculate. So acceleration is change in velocity over time. That's the definition, is the rate the velocity is changing. You could think about it as the slope of the velocity versus time graph, because meters per second divided by seconds is going to give me meters per second squared. Or you could think about it as this, can't see, this equation right here. To get acceleration, I would subtract the velocity over it and divide by the time. So the change in velocity, or the rise, if you're thinking about it in slope, from this time to this time is 10. And it's tempting to put 2 seconds here, but these each represent 2 seconds. This is actually 4 seconds. So